So I felt like it would be nice if then I don't have to reteach anything.
Is anyone taking like the...
No, everybody found a home in a regular section now.
Yeah.
Praise God.
Yeah, Chris liked it though.
It's kind of nice.
Yeah.
I mean, if you can handle it to be self-paced like that you can do what you want. Okay, so what is the purpose of a redox reaction? Does anybody remember?
Yes.
If you guys don't stop talking, I'm going to put you in the hot seat. Joseph! The purpose of a redox reaction is to generate electricity. Remember that electricity is also known as current, which is also known as the flow of electrons. Since electrons are transferred from the oxidized species to the reduced species, if you can set up a redox reaction in a proper way, you can harness that electron movement and turn it into electricity, which is what your batteries and your phones are doing right now. Okay, so how does this happen? How does this generating of electricity take place? The answer has a special name. It's called a Voltaic cell. Oops, my dyslexia got to me. The Voltaic cell is also referred to as the galvanic cell. Those words are sometimes used interchangeably. So if you ever see that word galvanic cell, it means the same thing. But also, the word that you know for a Voltaic cell is a battery. So a battery in order for it to be a battery by definition, it has to utilize a chemical reaction to generate electricity. And so that's really what we're going to learn about today. So a Voltaic cell, though, has to be set up in a proper way. If you have in the same reaction container your oxidized and your reduced species, a reaction will take place. But if it's happening all at once, you're not able to generate electricity from the reaction. And so think about any time that you see anything that's tarnishy, that is a redox reaction. So like if you have rusty bits on your car, that's a redox reaction. If you have jewelry that has to get polished because it's looking kind of dull, that's a redox reaction. What color right now is the Statue of Liberty? Do you know? It's like green. What color did it start out as? Copper, yes. It actually did not always look like this. So that what we see is a redox reaction. None of those processes generated electricity, though. So how is it that you're able to generate electricity with some of these reactions and not all of them? It's just how you separate it and how you set the reaction up. So in order for your Voltaic cell to generate electricity, you have to keep separate the things that are reduced and the things that are oxidized. Yes, you should draw this. Okay, so this is my representation of the Voltaic cell. Always on the right will be the place where reduction happens. Why? Because that's the way we always draw these things. And then it's easy to understand that or to remember it. R for reduction, R for right side. So the reduction occurs on the right side of the battery. So then what must have to happen over on the left? That's your oxidation. Okay, so what is in these like two little separate containers here? You have these rectangles that I've drawn on here. These are metal electrodes. Do you know what an electrode is? Have you heard that word before? It's something that conducts electricity. Metals are an excellent conductor. There are other things that are conductors as well. And then there are things that are insulators, which is the opposite. So they stop electrons from flowing. Metal conducts electricity, but most plastics are insulators. And so that's why we see wires wrapped in some kind of other material, because that prevents the electrons from leaving the wire and just going randomly out into the atmosphere. So there's a metal electrode on either side of the separated parts of my battery. And then when I drew my little containers, I drew like wavy line. That's to indicate that there's something juicy, some watery solution in the container. So what occurs in this part of the reaction is oxidation. So I'm just going to give an example of this. Let's say, what kind of metal do you want me to use here for the electrode? Give me a metal, any metal.
Nickel.
Nickel? Okay, so then my electrode is made of nickel. So how would I show an oxidation reaction? This is what it would look like. Nickel from this metal bar, so atoms from this metal bar are going to lose electrons and form, usually nickel is a +2 in solution, so we'll use that. So the nickel will actually be used up. That bar will start to disintegrate a little bit, and what will happen is that as it's used up, it's going to produce electrons and ions in the solution. Nickel is really lovely, and it turns green when it dissolves in solution. And so you would see, as an observation, that you would start with a clear colorless solution in here, and as this bar was like being used up and dissolving, really, it would turn the solution green, which would indicate that you would have a presence of this Ni2+. That's what oxidation is. It's the loss of electrons. Yes, sir?
So then what would be the solution?
It depends. Usually you would have a solution that would have, pretty much anything that you wanted it to be, as long as it didn't form a precipitate. So like you wouldn't want to use sodium hydroxide because nickel hydroxide would be insoluble. Okay, so what's going to happen to those electrons? They're not going to stay in the solution. They're going to go someplace. If we connect the two electrodes using a voltmeter or any other thing that can conduct electricity, mostly when you see these drawings, you'll see that the voltmeter is what connects them. What's a voltmeter? It's a little device that tells you how much electricity is passing through something. So if you want to test if your battery works, you hook one end up to either end of your battery and turn this thing on, and it'll tell you if electrons are flowing through it.
These like batteries?
Yeah. Yeah. So that's what a voltmeter is. In the lab, we use voltmeters because we want to know how much electricity is going through, so that'll quantify the number of electrons that are passing through the wires. In real life, though, a battery, we know, like when it's connected, it means that you're like turning on your device and using it. And so when that connection is made, electrons can travel through the voltmeter. How do the electrons travel? They're going to go through the voltmeter, over across into the other wire, and then they're going to hit the other metal electrode. They have to go somewhere though. They can't stay on the metal rod. So they'll reduce whatever is taking place in this reaction. So what metal do you want me to use for this electrode? Choose anything but not nickel.
Mercury.
Iron. Iron is more better because than mercury. Mercury is a liquid at room temperature. And so it's hard to get that to be something that'll be workable. Okay, so what does a reduction look like? In this solution, there will already be ions of iron floating around that are like in contact with the electrode. And so these ions, when they see that electrons are present, and I wrote 2 there, you don't need to worry about that. Eventually we'll talk about it, but not today. So one of those iron atoms is going to pick up 2 electrons, and then it'll turn into iron. And so what will that mean? It'll mean that you'll have all of these new iron atoms that will form onto the electrode. And so whereas on the oxidation side, you're going to use up some of that metal, and after you look at it again, it'll look like a shriveled up little thing there because you're using it. You're taking those solid particles away. On the other side, this will gain mass. This iron electrode will gain mass, and so it'll look like there's like a growth on that electrode because ions from the solution now have turned into solids, and they conglomerate or form onto the metal electrode. So here I'm showing that my substance is oxidized because it gave away 2 electrons. Here on the reduction side, I'm showing that the substance was reduced because it picks up these 2 electrons. So this is something really important. If electrons are a reactant in your little reaction like this, the substance is reduced. So again, this is something that's easy to remember because of the letter R. If electrons are a R reactant, the substances are reduced. So hopefully that can help you to remember those things. It is something that you kind of do have to memorize, but like I said, it's easy to remember. Okay, so I've not drawn one more part of the voltaic cell, and it's like one of the more important things. So I'm going to use the rainbow pen to draw like a little rainbow here in between the 2 components of the voltaic cell. This rainbow bridge here has a special name. It's called the salt bridge. And if your voltaic cell does not have a salt bridge, your battery cannot run. It'll never be good at conducting electricity. Let me explain why. When the very first electron leaves this electrode and is transferred over to this side of the battery, you're going to have a charge buildup that's going to prevent anything else from happening. So here's an electron. What is the charge of an electron? It's negative. So if this electron just moves on its own and nothing else happens, no other electrons will travel along the wire either, because electrons are repelled by each other. And so if they are not, since they can't get along, no other electrons will come over here. So we need to do something to alleviate this charge buildup, and that's where the salt bridge comes in. So the salt bridge is made up of ions that are not reacting. So I'm going to write, it contains non-reactive ions. Typically, K and NO3. K plus and NO3 minus. And so they're juicy. It's a solution. So what will happen then is that those ions will be able to move in between the two parts of the battery to break up that charge buildup. Okay, so when one electron comes over to the right side, an oppositely charged ion is also going to go that way because opposites attract. So the potassium will move over from the rainbow part. Potassium will come over here into this beaker or into this side of the reaction. If there's one potassium and one extra electron, what would be your total charge then? 0. So then that means that another electron is able to come. So every time an electron comes over, a potassium also comes over. Now the same thing happens in reverse. Once one electron leaves here, what would be your charge on this piece of metal? +1. So you've got this positive charge here. And so which one of the two ions then will travel to the left? The NO3 minus, yes. And that's what will take care of that negative or that positive charge there so that more electrons can keep moving from one side to the next. So you have to have the salt bridge. That's what its purpose is. It's just to mitigate charge buildup. All right, so we just picked a random battery. We chose nickel on the left and iron on the right. Let's see if this is something that would actually turn our devices on. So to know how good your battery is, we need to be able to know what it means when we combine the two parts of the battery. And so to do that, we're going to use this simple mathematical equation. I want you to write it down in your notes and then I will explain all of it. The little circles in the upper right corner of the big E's are like the degree symbol. Okay, so E degrees cell is what we call cell potential. Do you know what the word potential means? Mason?
What could be?
Yes. So what could you do? How much energy could you make? These little degree symbols here indicate that you have standard conditions. And so what does that mean? It just means that you're operating at a specific temperature, at a specific atmospheric pressure, so that you can compare apples to apples. You don't need to know what standard conditions are yet. We'll talk about that when we get to the gas laws in a couple of weeks. All right, so then what is E red? This is the energy generated from the reduction. How will you know what that value is? You'll have to look it up on a table. That's the new sheet I'll give you in a moment. EOX is the energy generated from oxidation. How will you know what that value is? You'll look it up on the table. Okay, so in order to figure this out, we're going to need to have chemical equations for both of the things that happened in our battery. So on the left side of our battery, we had nickel. The nickel solid, that electrode was going to break down and it was going to form nickel ions and release 2 electrons. That's what was happening on the left side. What happened on the right? Well, we had an iron ion that was in solution that picked up those 2 electrons that were put off by the nickel and formed solid iron. We know that this is the oxidation because it was on the oxidation side of our drawing. We know that this is the reduction. So what is the value of EOX and E-red? I have a light pink sheet for you to help you with that. Oh, thank you. Oh.
They smell me at your head. Yeah, move your head.
Why don't you just stand up? Move your camera. Everybody has a light pink sheet? Okay, so look at this. There's a front and a little bit of a back.
Oh my god.
Yes, I know. There are many things on here. Okay, so this is part of being a scientist. You have to be able to find data from tables like this. Yes, I could put this as a Google Doc for you on Google Classroom where you could just Control F and find the things that you were looking for, but that would take all the fun away from it for you. So I want you to learn how to find things in a table like this because scientists, that's where we get information from. Stuff like this is impossible to Google. Even with the great algorithms that Google is able to produce for us, if you're a scientist and you're actually looking at knowing information like this, where do you go for it? If Google's not an option, you have to have one of these. This is the CRC handbook. It's the Handbook of Chemistry and Physics. I call it the Chemistry Bible because literally these are Bible pages and the print is like 4-point font. And so one of these pages is probably like 30 scientists' life work. And all of this information, this is like maybe 3-point font. It's incredibly small. And so when I need to know information that I don't already have like typed in a nice list like that for you, I have to go to here and I have to be able to figure out where to find it and read what is all of this nonsense. So you need to learn how to do that as well. All right, so let's find, these are 2 simple ones, so they should be relatively easy to find. Let's find something that looks like the iron. We'll do that first. Okay, so where can we find that? I found it. It's on the right-hand column of the first page, of the front page, I should say, about a third of the way down. We're looking for this equation. Do you see it as well?
Well,
It's so the numbers are in numerical order. It's negative 0.44. Do you see it now? What's the unit for this number?
0.
What's its unit?
For what number?
All of those things in that table have the same unit. It's big V. V stands for volts. Okay, let's try to find the other one. You're looking for nickel.
One seems like a negative type thing. The right one seems like positive.
I'm being hasty. It should be on here. Oh, I found it.
I didn't find it yet.
It is, and it is backwards. So I'm going to write down what I see on this table exactly the way that I see it.
Rewriting it.
Yes, you should. And then my value is negative 0.25 volts. So why is it backwards? Why isn't it on the table the way that I see it on my paper? I was looking for this equation, but I found the backwards equation. Look at what the top of this chart tells you. What is the title of the chart? Standard reduction potentials. So everything in this list is a reduction. We could write all of the equations as both reductions and oxidations, but then there'd be twice as much data. This isn't even all of them. This isn't even all of the reactions. There'd be twice as much data, and how would you know where to find anything? It would be even more complicated to find what you're looking for. So these are just listed as reductions. If you see your equation on here, but it's opposite of what you have written on your paper, that's how you know that's the oxidation. So if it's opposite to here, O, it's oxidation O. In the same way that if the reactants, if the electrons are a reactant, R, this is a reduction, R. Mason.
but the potential is the same.
It is, because in my equation here, I'm going to subtract the value for the oxidation. And so what I'm really doing is flipping the sign. Because that's what subtraction does. All right, so let's calculate this and see if we have a viable battery. So the math of this is easy. But I'm going to have to subtract a negative number. So what do you do when you're subtracting a negative number? What is that actually? That's adding. Good. I'm glad that your math is strong. So I'm going to add, and then my number that I should get is, good. What's your unit?
Volts.
Big V. Okay, so that's my answer, but now I need to decide, is this something that's going to make a battery? Is this going to power a device? So when we're working with energy, we always have to know the sign convention. What that means is, what do we mean by when something is negative? What do we mean by it when it's positive? The sign convention for the reduction potentials, if E is positive, you have a spontaneous reaction.
We have to write this down.
You should know it. If I write it, you should write it. That's a pretty good rule of thumb. So what does spontaneous mean? It means that it'll do the reaction on its own without you having to do anything to add energy to your system. Do you want a spontaneous reaction if you have a battery?
No.
It's not going to explode. It just means that the reaction will progress. Yeah, that's what I'm asking. Do you want your battery to work without you doing anything to it?
No.
I think you do. I think you want to put your battery in a device and for it to turn on. A non-spontaneous reaction is one that you have to add energy to. And so if you have to plug your phone in, that's an example of a non-spontaneous reaction. You have to add energy. Yes, Elliot? You can. If you have a battery that you have to add energy to, you don't have a battery. Or you're charging your battery so that it can run again. So is this spontaneous or non-spontaneous?
Non.
It is non-spontaneous. So is this a battery that we want to put in our phone?
No.
No. No, no, no. Okay, so what happens when we get a problem like this on our homework? How will we know what to do? Let's do some so that we can answer that question. Okay. After today, you'll be able to complete all of these homework pages. There are, again, only 3.
How many ones is due?
This is not due until Tuesday of next week. Next class, we are going to be doing an experiment.
What are we gonna be doing?
We're going to be doing this, but in the lab.
Hello. What? Shit.
All right. I want you to listen carefully because this is how you'll not do well on this homework assignment by not following these directions. Okay. For each of the following reactions, calculate E cell and state whether the reaction is spontaneous or non-spontaneous. This is how I want you to show your work. So A is the first one. I'm going to recopy it, but you do not need to. Okay, so the first step is to break this up into 2 separate processes. That's the only way you'll be able to find it on your pink sheet. So how do I know what the processes are? Well, how do I know how I can separate this? I'm going to find the elements that are the same or similar and take those out of the equation. So let's just do the chlorine ones first. So I'm going to have ClO3 minus, arrow, ClO4 minus. Why do I need to do this? Because, the top reaction is the overall redox reaction. I only want to look at the reduction and the oxidation separately. So then I need to do this for the iodines as well. Do you need to do this on your paper? Do you need to show this work? Yes, you do. Okay, the next thing that you need to do is find these equations on your light pink sheet. All right, so first I'm going to try to find the ClO3. It has to be as close to exact as possible. So I'm looking at the left-hand column, and like here, I see a ClO3 minus, but it doesn't have what the other side of the reaction is the same. But if I look down a little bit farther, I see that this reaction,
How do we know which one to use? Maybe it's one.
I'll explain that. That this reaction, while it has a lot more junk in it than my original one, it's like got the main things. The one that I saw earlier on the list looked like this. And so this was all okay. Nothing in there about the H pluses. Oh, and then it's got the 5 electrons. That's fine too. That's fine. Doesn't matter. Doesn't matter. But then it has 1/2 Cl2. And that doesn't appear in this reaction at all. So that's how I knew that I couldn't use this as my option. Okay, so I did find this though. What is the value for E from my chart for this reaction?
What's this one?
It's the 1.19 positive. So now I can decide right away if this is the oxidation or the reduction. Is ClO3 minus in the same place here as it is in the second reaction? No, it's on the opposite side of the equation. So remember, if it's on the opposite side, it's the, good job. Half done. Find the other equation and write that down as well. Oh, it's 5 from the bottom on the left side. Do I need to write that equation down? Do I need to copy it off of the pink sheet? Yes, you do. Mason.
When we copy it, would you let us do / be graded on whether we include the state of matter?
You don't need to conclude them. I will not mark it wrong for that. On my answer key, I have all of the states of matter written, but I'm a little OCD about it. I don't expect you to do it. So what I did here, you can do as well. The E value for this, according to the chart, is
0.5.
correct.
Okay.
Is this the oxidation or the reduction? It's the reduction. How do I know? Well, the other one was the oxidation, so process of elimination.
Wait, how do we know it was oxidation?
Because here, my ClO3 minus, Joe, is a reactant, and here it's a product, and so if it's in an opposite place, opposite O,
Oh.
oxidized O. I'm almost done. I just need to do my final math. E cell is equal to E reduction minus E oxidation. Write this down like kind of big at the top of your paper. And once you do that, you don't need to write it every time. So my reduction is my plus 0.53 volts. I'm going to subtract my positive 1.19 volts. And my answer should be negative 0.66 volts. Here I calculated the cell potential. That's the first order of business that I need to do on my homework problem. And then it asks, is this a spontaneous or non-spontaneous reaction?
No.
How do you know? It's negative. Can't spell. So that's another thing that you can use to remember. Negative N, non-spontaneous N.
That makes sense.
How was
So
this?
if it's negative, it's not spontaneous.
It's
Yep.
good. It's good.
It's not bad. It's a little tedious. It's a little tedious. But like the work of it is not bad. Like this kind of math, weak sauce. You can manage this. Would you like me to do another one?
No. Actually,
Which one do you want me to do?
The hardest one.
The hardest one? Let's see if I can find any ball busters. H. All right, so for mostly all of them, there are 2 reactants and 2 products, but then I threw this friend on here. What the bleep? What are we gonna do? All right, so this is what I'm gonna do. I'm going to take one of my reactants, the Br minus, that's the first one, somebody use that. And then I only have 1 product, but I have 2 of it. So I'm going to use it as the product for the first half reaction, and then I'm going to use it for the product in the second half reaction as well.
Number 8.
Okay, so I need to find both of these reactions on my pink sheet and hope that they're something I can make sense of on my mind. I'm looking for Br minuses, and if there's 2 right here in this equation, there's probably a bunch on this sheet. Okay, Br minus, I found this first one. I found this like maybe a third of the way down on the left. Again, you need to write this. Why? Isn't this just busy work? Well, I mean, a little bit it is, but you need to be able to write this down so that you can compare it to your original equation. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's like the 16th one down. And it's plus 1.44. Okay, so is this the oxidation or the reduction?
Oxidation.
How do you know, Mason?
Backwards. Br feeding against the center.
Yes. So if I'm looking for Br minus, this is my first thing. If it's in the opposite place, it's the oxidation. So that means that whatever I figure out for this thing has to be the reduction, right? Because there's only 2 options. So process of elimination. All right, let's go hunting for this next one.
Br sub 2 plus 2e electrons to 2 Br minus, would that work?
Wait, say that again?
It's Br sub 2 plus 2 electrons, reaction arrow to Br negative. Br minus 1.
Nope, that doesn't work because it has to be this. Let me see what I put on my answer key. Is this one not even on here? Hang on a second.
You know, as a good fellow scientist,
Yeah, we better hold off, Mr. Shook.
I think this is that trick.
1.08.
That one's 1.07.
Oh,
Why don't you do that one?
I'm an idiot.
Yes. What?
Shoot. I don't know what I'm doing. So let's just use 1.08 and call it a day. Let's pretend we found it. My bad. I'm glad that I chose this one. So when you make your own homework assignments, you have to write an answer key before you send it to the printer. I did do that. I just forgot to change where my error was before I fixed it, and then was like, oh, it's fine. Let me just print it. Dummy. Dummy.
Which one is that?
This is H.
We're gonna do 1.8.
Okay, so if this was a real thing, what would you get for an answer?
Negative 0.362.
Yeah.
And so was it spontaneous?
No.
So,
My bad. I'm sorry. Okay, you have enough time to work on this now, or I mean, you have enough knowledge to work on this. You have the whole rest of the day as time as your own, but I am going to give you the lab for Friday, since you'll need to write it in your lab notebooks. So that's a thing as well that you'll need to accomplish. Oh, I'm sorry, Ray. One also for Megan. You have a goodly amount of time, but you do have a goodly amount of work also. I mean, Elliot, are you okay?
Yeah.
You have a headache tonight. I'm sorry. Yes. Oh, there's two of the exact same thing?
One looks like it.
Well, one's like 0.1 different.
Yeah, 0.01.
Oh, yes, I see the permanganate.
It's actually
You can choose which one you want.
You need a balances.
Is that the right one for B though?
Probably.
It has MnO4 and MnO2.